Hey guys, today we're talking about spherical and cylindrical integration. And in order to do that, we're going to establish three things. So first thing's going to be intuition about how these systems work. Second thing's going to be converting back and forth between them. And third thing's going to be getting our volume forms. In this video, I'm not going to show you where the volume forms come from. There are other videos for that. Here, I'm just going to kind of add them to the conversions. So first things first, I made a little toy to give us some intuition. So here's my little toy. In this first folder, I've got rectangular coordinates. So I want to describe how I get to a point in space using rectangular coordinates. So you guys are super familiar with these. First, we're going to go over some distance. Then we're going to go back some distance. Then we're going to go up some distance. Traditionally, we refer to those as X, Y, and Z. So here I'll call them X, Y, and Z. You'll notice that in my sketch here, my little point that I've arrived at has a ZR in the Z spot. That's because Math 3D doesn't like it when you name variables the same thing. So this is the Z that goes with rectangular. Normally, I would just call this a point X, comma, Y, comma, Z. So there's my point. We get there by going over in the X direction, over in the Y direction, up in the Z direction. Check, done. You guys are familiar with this by now. So let's talk about how we get places in rectangular. I'm going to turn rectangular off, and sorry, I said rectangular. How about cylindrical? So cylindrical is going to be a lot like a polar analog. So the first thing we're going to do is we're going to go over an angle in the XY plane. Then we're going to go out a distance along that angle. So in this case, we're going out, let's see, R is set to 3.8 right now. And my angle is set to like a radian and change. So then our next thing's going to be, now that we've established a point in the XY plane, we're going to go up or down to our Z value. And that's going to give us our point here at the end. So cylindrical is really just polar, but with a lift, right? So polar plus. Okay, so I'm going to turn all that off. And now we're going to talk about spherical. And spherical is going to be a little bit of a head twist. So first things first in spherical, I'm going to pick two angles. I'm going to start with the one in the XY plane here. And I'm going to turn that guy back down a little bit so we can see it a little easier. So that angle's off the x-axis. It's in the xy plane. You can see that. So that's a theta, right? In this case, I've got a theta for theta sub s in my code, but that's really just a spherical theta as opposed to a cylindrical theta. The thing about them is they mean the same thing, right? They're the angle off of the x-axis in the xy plane. So that's our first angle. Our second angle is going to come down off of the oops, that's not the right one. It's going to come down off of the z-axis. I'm going to swap that order so those make sense. So you can see that's in the plane that I went to with my theta angle, and then I came down off the z-axis some amount. Now those two things actually describe a line in space, and then we're going to go out that line a distance. So if you look straight down this thing, right, your theta in the xy plane, right, and this thing that's acting a little bit like a radius act in sort of similar ways. But we can see that's not actually the radius in the plane. The radius in the plane's a bit shorter, right? So I'm going to grab this thing quick because I want to show you where this comes from. So drop that into OneNote here. Okay, so I want to, in here, grab this little triangle. So I want to think, well, what if, whoops, that's not really very straight down, Joe. Let's pretend we dropped this straight down, right? There's a line coming out here. That goes to a point in the XY plane. Start trying to find my eraser. And we could see there's a little right angle here. This line here is like the R, right? This line here is actually a rho. It looks like a kind of a slightly off P. that rho is the kind of cylindrical radius, right? Or the spherical radius, right? The r is actually the old cylindrical radius. And then this other distance here, I bet you guys could tell me what that is. That's actually just the z coordinate, right? So there's a conversion here that I could figure out. One of the things I want to figure out is what is this r? So I'm going to actually take that black triangle and I'm going to copy it up here to make a red triangle on the opposite side. You guys see that? So that red triangle is just a black one, but copied to the other side. So this is still the z here. And this is now the r up there. And so I'm going to write down a conversion factor. There's a couple of things I could figure out from this. I could figure out the not very useful Pythagorean theorem one, right? Which is that rho squared is r squared plus z squared. That one doesn't turn out to be super useful. Not that it's not true, just not super useful. The one that is really useful for me is to notice that this r is on the opposite side of this little triangle from the angle, right? That's my angle phi there. So I could say something like, oh, r is rho sine phi. And I could write down something like z is rho cosine phi. Now, I'm going to start just kind of bopping out a bunch of conversion factors. This one between cylindrical and spherical is the only one between cylindrical and spherical I'm going to, well, maybe this one. These two between cylindrical and spherical are the ones I'm going to use for that. I don't have a ton of opportunity to switch back and forth, but you'll find it occasionally useful if you remember these. The place I really find this most useful is just remembering the x, y, and z. So these are going to be coordinate conversions between cylindrical and rectangular. And over here, I'll write spherical back and forth to rectangular. I want to start with a couple we know. A couple we know are that x is r cosine theta, and y is r sine theta, and z is z, right? Those are the same z values. Okay, now the cool thing is with these two conversions from just looking at this one triangle, so I can make some more conversions. I'm just going to actually plunk these guys in, right? So I'm going to say x is, well, it's whatever r is, which in this case is rho sine phi, times cosine of theta. And then y is rho sine phi, because that's r again, right? Times sine theta. And z is rho cosine phi. Students have a lot of trouble remembering these because they're kind of flip-floppy. It's real easy to forget which one goes with what. Instead of looking in the book every time, you can just pull this triangle out of your head and use a little basic trick. I find that useful. You guys don't have to do this. You can. There's a couple other miscellaneous useful ones. So the miscellaneous useful ones that I sort of like are that rho squared is x squared plus y squared plus z squared. There's another useful one over here, which is that r squared is x squared plus y squared. I find those to be pretty darn useful. You can square root both sides if that makes a more meaningful identity for you. Personally, I like them like this. Now, our last thing is learning our integration. So remember how in rectangular, d volume is dx, dy, dz? Well, in my new coordinate systems, I'm going to also have dv's. The dv for cylindrical is actually pretty chill because I could kind of look at d volume in rectangular and say, well, dx, dy is actually d area. And then I could like also do a dz after that, right? So a way I could write d volume in cylindrical would be to write polar area, which is r dr d theta, and then throw a dz on the back end for good measure. That'd be good enough. For spherical, spherical's a little harder. So there's the thing you can do with a melon. I want you to watch that video. I'm just going to write down what we got here. What we got was a rho squared sine phi d, and now I need the three variables. So the three variables in spherical are d theta, d phi, d rho, and these could be in whatever order. So depending on your kind of integration situation, you might find that these orders matter a little bit. I'm going to let you guys go explore the video for where those volume forms come from. I would prefer it if you watch the one about cutting a melon or something first before you watch the formula one. I don't find that the formula means much to students without actually having looked at kind of cutting a melon. Thanks, guys. That's what I got for today.